Okay. Hi, everybody. Glad to see you again. It's been a while since we've done these broadcasts. Hopefully you can hear me. I have someone here who will tell me if you can't, but I guess I can just get started. So the assignment this week is to create a class to build an RSS feed reader. So I thought that today's session will be just about building a smaller, simpler class for the rational class as the text of the problem I put online stated. So let's just begin. So first I'm going to open my canopy and so I just wanted to, before we begin, I just want to mention I read the comments that everyone had on these coding sessions through the question on the final exam. Thank you very much for sending those in. One of the main things that I think was, one of the main issues that was raised was that these videos are actually kind of long, just to go through a coding session just step by step like this. It's pretty long and there's some parts that can be cut out. So I think what I'll do in the future is I can create another, I can leave the full video up, but I can also create another video which will have the important parts and maybe put text on top and just make a sort of 15-minute version of the same video for those who just want to get a gist of what's happening. Okay, so let me first copy the text and like that. And let me share my canopy. Okay. All right, so let's just write this down just so we know what's happening. All right, so the main class that we're going to build is this rational class. And the rational class is supposed to represent a rational number, and a rational number has a numerator and a denominator. So if we want to just draw a quick picture here, let me screen share Paint again. As always, it usually helps to draw a picture. So a rational number is something like A divided by B, and that's basically it. So this is the numerator, and this is the denominator, like that. All right. So this image will help us in the future when we have to do the calculations between rational numbers. All right, so how do we begin writing a class? So first of all, why do we want to create a class? Well, we want to create a class because we want to create our own objects, and in this case, the object that we want to represent is a rational number. And in Python, everything is an object. The objects that we've sort of seen way at the beginning of class were these very primitive objects. They were integers, strings, floats, booleans, things like that. So we can represent more complex objects that do anything we want using these primitive types. So in this case, we're going to represent the rational object using 2 integers. So we can begin by saying class rational. And in Python, everything inherits from the object type. So we usually write that in, but you don't have to write object in here if you don't want to. Okay. And the first thing that we have to define for a class is the init function. So this is the function that, or the method, sorry, the method that is called when the user creates an instance of a class. Okay, so what I'm writing here, this class definition, is actually an abstract view of what our function can do and what data members our function has. An instance of a class is a particular object that has specific values, and yeah, so we can say something like def init, like this. And when we create an instance of an object, that's when this init function, init method is called. Sorry, so I keep saying function versus method. So functions and methods are the same, except that we call something a method if it's the function of a class. So yeah, okay. So we say def init, and we always have to have this self, and this self refers to so when we access the class, we have to have some sort of handle on a particular instance of the class. And by convention, we call this instance self. And as we do operations, when we create this definition of the class, we usually refer to the self. And when we create an instance of a class in the future, this self changes to whatever that particular instance is. So we can say self. And what does our rational number have? It has, when we create it, we're going to create it with two parameters. One is the numerator, so we can call it the num, and the denominator, so denom, like that. Okay. Okay. So what do we do in the init function? The only thing we do here is we assign the variables that the parameters from the init function to the data members of this class. And naturally, the data members should be a numerator and a denominator. That's how we're going to represent a rational number. So we say self dot the n is equal to num, and self dot d is equal to denom. Okay. So with these two lines, we have created two data members of the class rational. The data members are n and d, and we have assigned them to be num and denom, which is the parameters that the user will instantiate an object of type rational with. Okay. So that's pretty much it for the definition of this rational class. It's not too complicated. If we were to create a more complex class, we might have other data members that are of other types. So we could have, they don't have to be primitives. In this case, they're ints, but we can have a more complex class of, I don't know. I can't think of anything off the top of my head, but it can be another class, another more complex object. Okay. So with this definition, let's go outside of the class and let's try to create a rational object. So we can say something like R1 is equal to, and by doing the following, we are creating an instance of a rational object. And so we can say R1 is equal to, so this is going to be our variable name. And here we're going to say, we're going to call the rational class. And as soon as we do this, it's going to call the init class, the init method. And the init method takes two parameters. So the self refers to the instance of the object, which we're already creating. So that's why we don't need to give it as a parameter. So we only have two parameters to give, the numerator and the denominator. So we can say something like 2 and 5, like that. So this line here, line 14, creates an instance of the rational class called R1. Okay, now what would happen if we were to print R1? We would like it to do some sort of pretty printing, 2/5, so that we as users can clearly see what the rational number looks like. But when we do this right now, what actually gets printed is just the fact that R1 is a rational object at a specific location in memory. Okay, so this isn't very user-friendly, right? Okay, so that means that we have to create some sort of method inside our rational class that knows how to handle this keyword print when applied to a rational. Okay, so how can we do this? I think we have seen this before in the lectures, and there are these special functions that start with underscore underscore, much like this init. So these special functions these special methods get called when we do certain things with these objects. So this init method, underscore underscore init underscore underscore, was called when we created an instance of the rational class like this. We can have, and then the special method that's called when we say print, for example, on a rational number, is underscore underscore str for string, like this, and we say self. And we only say self because when we print, the only thing that print takes is the instance of the rational number. It doesn't take any other parameters. So the only thing that Python implicitly knows that this instance of the rational number is supposed to be self. So we don't need to give it any other parameters. Okay, so this underscore underscore str method will be called whenever we use the keyword print on a rational number. Okay, so what do we want this to do? Well, when we say print R1, I think the best thing to do would be to print something like the numerator divided by the denominator. So we can say something like self.n. And notice that here I'm using the data members of the class because the self dot n, it refers to the fact that n is a data member of the class rational and d is a data member of the class rational. We no longer know anything about num and denom. These were purely just known in the scope of this init function. So from now on, we refer to the data members using self.n and self.d. Okay, so when we print, coming back to this, we want to print the numerator plus maybe a slash plus self.d, like that. So now when we do this, it should print 2 divided by 5. Okay, so let's see. So the error that we get is a type error, and the line is at print R1, and the line that it's unhappy with is this print self. I see. Okay, so I think, so since this is a method, it actually has to return, and I've done this error before many times. So we have to actually return the thing that we want to print, not just print it. Okay, so this should work now. Okay, and we have one other small error. So in this case, we're trying to concatenate a string with an int. So we're going to have to say str and str like that. So we're basically casting or converting the type of self.n, which is an int, to a string, so that we may concatenate it with another string. So that should be okay now. Excellent. Okay. So in this case, notice, just to reiterate once again, when we called print R1, the keyword print goes to the R1 is a rational type object. We go into the rational class. Do we have some function, some method called __str defined? Yes, we do. And go ahead and execute whatever's inside it and put the results on the console. Okay. So I think the first thing that you generally do when you create your own custom class is to create, even for just debugging purposes, an __str method. That way you can just easily just print print your variable just like you would print an integer or a float, just to see what their values are. It's very useful for debugging purposes. So just as a general, that's what I tend to do. It's just to create an str method. Okay, so this is nice, but we should probably add some functionality to our rational class. And we can add this functionality by, so rationals are numbers in math, and usually when we deal with numbers, it would be nice to be able to add, subtract, multiply, divide them, things like that. So what we would like to do is to be able to say something like, R1 is equal to that, R2 is equal to maybe 4/5, and we can print R1, print R2, and then we can say R3 is equal to R1 plus R2, print R3. That would be very nice to do. So much like the print has its own special method name, all the mathematical operators have their own special names as well. So we can, I don't remember off the top of my head what they might be, but with enough practice, we can figure it out. So let me go to, so what I would do in this case is I would probably go to Google and I would say Python add objects special method, something like that. So we can look at, I guess, the documentation might be a good place to start. So yeah, so here, special method names. So here was init, del, there's some some here, I guess these would stand for less than or equal to, things like that. So we can implement these. We could, some of these for example are useful for lists. So this __ get, I believe, implements the square parentheses for a list, for example. What else do we have? I'm interested in the mathematical operators. So here we are. Emulating numeric types. So here we have the special methods for the operators. So we have add is probably plus, subtract is minus, multiply, floor divide, and then divide here, true divide. Oops, in that. The difference. Yeah, I think we could probably implement div. So let's implement the 4 standard plus minus times divide. Let's try that. Okay, so let me switch back to Canopy. Okay, all right. So in order to implement the plus operator, so the special method in this case is the __ add, if I remember correctly. Add like that. And when we are adding, we're actually adding one instance to another instance. The first instance is ourselves. So it's the number, it's the object that we're calling this function with. And the other instance is for example, I can call it other rational. So when we call something like R1 plus R2, this plus will be called on R1, which would be self, and R2, which is other rational. Okay, so like with this, we can even add, implement the plus operator between 2 rationals, like that. Okay. So I think now we need to just think about the math for a little bit. So if I am showing you everything that I'm going to be doing, I'll go back to Paint and I'll say if I have a rational number A and B, and then C and D, like that, then what we do is to add them, we do this plus this times this, plus this times this, divided by this times this, like that. Like that. That's probably better. So that would be the formula for adding. Subtracting would be this plus gets changed into a minus. Multiplication is just multiply AC divided by BD, and division similarly. So I think that's pretty standard math. So let's go back to Canopy and implement that. Okay, so to add, we need to create a new numerator and a new denominator. So new numerator is equal to, in this case, so what did I say? It's going to be the numerator of self, for example. multiplied by the denominator of the other dot d plus the self.d times other rational n. So that's our new numerator, and our new denominator will be the two denominators multiplied, so self.d multiplied by other rational dot d. Okay, so now in our hands we have a variable that holds the new numerator and the new denominator. Now this add is supposed to return something, so we'll return. And what do we want to return? We want to return another rational number, or another rational number whose numerator is the new numerator, like this, and whose denominator is the new denominator, like that. So notice that in this case, we're actually doing some, we're creating a rational instance inside our rational class, which is allowed, that's fine. Because when we're adding two rationals, we would expect that we'd get another rational back. So just like that. So I think that that method is fully implemented now. I'll expand that a little bit, like that. Okay, so now looking back in our code, which in the code down here where we do some testings, we created two rationals, we printed them. We know these lines work. We've tried this before. Now, when we do this line here, R3 is equal to R1 plus R2. Python sees this plus operator between objects R1 and R2, where both are of type rational. So we go into the rational class and we look to see if there's a method that is called __ add, and there is, because we just added it. We perform the operations inside it, which is these. Self being R1, I guess, and other rational being R2. Each one of these objects, since they're rationals, they have data members n and d, because every rational has a data member n and d. So that's why we can do these operations. And once the add is complete, we return a new rational object of type, with a value new n and new d. Okay, so that's that line. And then when we print R3, this calls the __ str of the rational object, because R3 was returned as a rational object. Okay, so let's run this, and perfect. So 2/5 plus 4/5 is equal to 30/25 according to calculations. 10 plus 20 divided by 25. Yes. Perfect. Okay. So hopefully that makes sense. Just for completeness, we can quickly add the other methods, which are basically the same. We're just changing what we do inside. So when we subtract, we do self.n times other rational.d minus that. The denominator stays the same. And when we multiply, we're going to have the new numerator is self.n times other rational.n. So numerator times numerator divided by denominator times denominator. And finally, div. So in this case, div is self.n multiplied by other rational dot d divided by self dot d times other rational dot n. I think that is correct. So yeah, just for completeness, sub is minus, this is times, and this is divided by. We won't do these cases in here, but hopefully these are correct. Now, one thing I didn't actually implement, and I probably should, is when dealing with rational numbers and division, it's probably a good idea to check for these weird cases where the denominator is 0. So what we can do is actually in our init function, we can add maybe a assert statement. We can say something like assert denom not equal to 0, and this will catch if we're ever trying to do something funny, to create something funny, and then we can put a error that says denominator must not be 0, exclamation mark, like that. Oops, like that. So this assert will just put a small check in place. So now if we ever try to do something like R0 is equal to rational 2 divided by 0, we should see an assertion error. So this will halt the program. This is an example of defensive programming where you'd rather crash the program you'd rather crash the program rather than allowing buggy inputs to go through. So just when in doubt, just crash and put a decent error message in there why you crashed. So let's take that out. Okay. So that's basically how we can create our own class. One other thing I guess that I wanted to create is a method for this class that doesn't implement one of these special these special keywords. So we can create a method which will simplify a fraction. So notice that when we down here, when we added these two numbers, 2 over 5 and 4 over 5, we got 30 over 25, which is okay, but it would be nicer if we were able to simplify it. So, divide top and bottom by 5, and you'd get, 6 over 5. So that would be a nicer number to display to the user than 30 over 25. So that's why maybe it would be nice to have this simplify function method. So this simplify method is going to be called using its name because it doesn't really implement a special keyword. So we can say def simplify self. Sorry, there's really nothing else that we need to do except simplify the instance of the rational number itself. And inside here, how do we simplify a rational number? Well, we could write our own code, and the way we simplify it is, notice that we would probably find the greatest common denominator. So it's the largest number that divides both of the numerator and the denominator, and divide both the numerator and the denominator by that number. Now we could write a program that implements that, and we would use recursion for that. I think that's a reasonable way to do it. There's lots of functions online that have already done that. Or we could use a function that's already written for us. So when you're writing classes, it's probably a good idea to look up if someone has already implemented this for you. So let's screen share the internet again, like that. And let's look for Python GCD. Let's see if that works. Okay, so we could look at the docs. Docs can sometimes be confusing. But there is a GCD method here from this fractions module, which returns the greatest common divisor of the integers a and b, which is exactly what we want. Perfect. So maybe we can just use this. Yeah. So let's just use that. Let's go back to Canopy. Okay. And in here. Okay. So in here, so GCD was in this module called fractions. So if we're ever doing something like that, we would have to say, we have to basically import those modules. So we can say something like from fractions import GCD. Okay, and now we can use GCD without having to rewrite it. So let's create a variable divisor is equal to GCD. And in this case, we want to find the GCD between self.n and self.d. Okay. Once we have this greatest common divisor, we can just divide the numerator and the denominator by that number to get the simplified fraction. So, sorry, new numerator is equal to self dot numerator divided by divisor, and the new denominator is equal to self dot denominator divided by the divisor. Okay, hopefully this makes sense so far. So all we've done is we've used another module that someone's already written to find the greatest common divisor, and we divide both the numerator and the denominator by this divisor, and this way we get our simplified fraction. So at this point we can just return a new rational with the new numerator and the new denominator, like that. Okay, so now we can print R3 like that, and then we can say down here in the code, we can say R3, call it S, is equal to R3 dot simplify. Notice that in this case, I'm actually calling this method simplify directly on an instance of my rational class called R3. Now, R3 becomes the self, and inside the simplify method, all of these self dots are accessing the data members of this R3. So R3 in this case will be 30 for the N and 25 for the D. Finding the numerator, I think, would probably be 5. Finding the greatest common divisor is 5. So then when we divide the numerator and denominator by 5, we'll return this new rational. And we can even print r3 underscore s like that. Perfect. So our simplify works well. So notice this was R3, 30 over 25, and R3 simplified is 6 over 5. So now if we want to, we can, in each one of these methods here, multiply, divide, subtract, and add, we could add a little thing at the end where after we get the new numerator and denominator, we can call simplify on the rational before returning it. But that's really, you know, this sort of decision would be up to you as the writer of this class. If you want to present the user with the final simplified version, or if you want them to have the, you know, the pure numbers from the calculations. Okay, so I'm going to choose to not do that just for time purposes. Now let's go over. I'm pretty happy with this rational class. Now let's go over a couple of inheritance examples. So one of the things that we could use inheritance within this rational class is to create a StringRational. So we'll create a new class called StringRational. Okay, let's spell that right. StringRational. And since StringRational inherits from the class rational, I'm going to put in parentheses that StringRational inherits from rational. That's what that means. Okay. So what does this string mean? So I can go back to you know, instead of drawing in Paint, let's just write down in here in our use cases what kind of things we want to do. So I want to say something like S1 is equal to a string rational. And you know, it's kind of tedious to write 2, 5, and it's sort of not, you know, intuitive to a regular user what the denominator or what the numerator could be. You might implement it backward. So we can, with the string rational, what I'm hoping to achieve is the user would give something like, I want to create a string rational that's 3 over 5, like that. So the user will give a string with 2 integer, you know, of the form integer / integer. And we can inherit from the rational class where we know how to do all these multiply, divide, plus, you know, all these other operations that we've created, except that we're just taking in a different form as an input. So if we want to make the most use out of our rational class, which we already wrote, what we should do is in our init method, we should really just maybe parse this string that the user gave, look for a slash, take everything before the slash to be our numerator, take everything after the slash to be our denominator, and we can call upon the init class, the init method of the rational class to create a rational number with these 2 values. So to put that into code, oops, like that. Our init will only take, this case, 1 parameter. And I'll call it StringRational, something like that. Okay. And with this StringRational, strRational, I want to parse it. So that means that I want to look at the string, use some functions, you know, that I already know for how to manipulate strings to get the numerator and the denominator from this string that the user inputted. So I can write a little comment for myself that says parse the string input to get the num and denom you know, I can also say a little extra work in the init, but can reuse rational. Yeah. So there's, if you're not familiar with it, I think this is a very handy function. So there's this function called, or method, I guess, it's a method called split, which can be called on a object of type string, which splits the string to give you a list of everything, all of the values that are in between the thing that you're splitting on. So for example, I can say split string is equal to, and the string that I want to split on is this StringRational. This StringRational is going to be something like, you know, string 3/5. And I want to split what the reasonable thing to split on. What character in my string can easily divide my numerator and denominator into two separate things? Well, it's this the character, the divide. So I want to split on the slash character. So once I execute this line, this split str is going to be a list. And the list is going to contain, in this case, the integer 3, the string 3 and the string 5. Okay, so now with these values, I can now just assign a numerator to be the split str at position 0. So this is going to be the thing before the slash. Oops, sorry, this should be num equals, and this should be denom equals split str at 1. So this num is, I'm not going to hold in this num variable this 3 in this case, and in this denom variable this 5. And when you split on a character like slash, the slashes go, you know, they go away, they disappear because you've split on them, so you don't care about them. Okay, so now that I have my numerator and the denominator already parsed, all I need to do is call rational.init, like this, with the instance of the class self, the num, which is this num here that I've just calculated, and the denom, which is this other one that I've calculated by parsing, like that. Okay, so at this point, this is going to call the rational init, and since I'm not defining any other methods in StringRational, everything that I do on a StringRational will be deferred to all of the methods that are in rational, since I'm not redefining any methods in StringRational. So now that I have something like s1 is equal StringRational, let's print s1. This should call the str method of rational up here. So it should just print, you know, 3/5 in this case. So let's see. Perfect, 3/5. Just like that. Okay, so now let's just quickly test creating another rational, s2, and print s1, print s2, and then we can also print sorry, we can say S3 is equal to S1 plus S2 just to test that those haven't broken. And then we can say print S3 like that. So let's run. Okay, so there's a small error. Let's see where. So it says that it is a type error, can't multiply sequence by non-int of type string. Line 20. So here I'm trying to do, where is this? Oh, I see. So it's trying to do self.n multiplied by other rational. So this is inside the add. It's right here. But that was okay. So the issue is here. So something's wrong because it seems that one of my operators isn't of type integer, it's of type string. So let's see, the issue must be in here. Aha, okay. So after I split, each one of these, each element in my list, so element at position 0 and element at position 1, are both going to be strings. So here I'm trying to initialize a rational number with string num and string denom. These should actually be integers. So what I could do is I can cast each one to an integer like that. And that should be better now. Yeah. So this was S1, this was S2, and this was S1 plus S2. Okay. Okay, so notice that in this case, in StringRational, all we did was create a new init function in which we allowed the user to write a more user-friendly version of the rational number that they wanted to put in. Okay, let's do a couple more classes, subclasses. So I said, let's do the class WholeNumber. So class WholeNumber rational. Okay, so WholeNumber would be something like W1 is equal to a whole number, and I would give it maybe, 6 like this. So that means that this would create, whole number is 6, which can be represented by 6 divided by 1, for example, if we want to represent it as a rational number. So this is actually an easier subclass than the previous one. All we need to do for this one as well is to just redefine the init function. So in this case, we can say this takes obviously self, and then number. Okay, and then in this init, we already know the numerator. The numerator is this number that the user gives, which is something like 6. And in this case, so what's the denominator going to be? It's always going to be 1, right? So when we call the init, we can again call the rational numbers init method, and we can say init with self, the numerator, which is number, and the denominator, which is 1. Okay, so W2 is equal to a whole number 4. Print W1, print W2. Not in between these, let's do print star 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 just to see the differences. That. Okay, and then W3 is equal to W1 plus W2 and print W3. Okay. Okay. So now if we run this, we should see 6 is represented as a rational number 6 over 1, 4 is 4 over 1, and when we add them, it's 10 over 1. Perfect. So these are sort of simple, silly subclasses, but I think it should demonstrate the types of things that you can do when you're subclassing. So the last subclass that we're going to look at is this mixed number. And this one's going to be slightly more complicated, but it shouldn't be too bad. So we can have a mixed number. Again, it's going to inherit from the rational class. And what is a mixed number? So mixed number is something like 1 and 1/4, something like that. So M1 is equal to mixed number. So we can represent the mixed number. We'll represent it, so you can choose to represent it however you want. Personally, I would represent it in a similar way that we did rational, so with three different parameters. So we can create like 1 and 5/7, something like that. So this will be the number 1 plus 5 over 7. I can just make a comment, 1 plus 5 over 7, like that. Okay. So what is this init going to do? Self. It's going to have 3 arguments. One is the whole part, one is the numerator part, and one is the denominator part. Now, in the previous subclasses that we've created, WholeNumber and StringRational, we essentially did, maybe a little bit of work. We extracted a numerator and a denominator, and then we called rationals init on it. Now, in MixedNumber, we could do something like that. We could do the work where we figure out 1 and 5/7 is going to be, 7 plus 5 divided by 7. We could do that. Or we could represent this mixed number using the subclass mixed number to have another data member. So I'm going to choose this way because it's going to be slightly different than what we've done before. So we can have the other data member be self.w is equal to whole. And so this is one data member. And then we can represent the rational part of the number. So this is going to be, this data member has the whole part represented with self.w. And then we can call the init function method of the rational class with the numerator and the denominator. Okay, so with these 2 lines, what happens is when we have an instance of a mixed number, M1 for example, here, let me put this up here. When we have an instance of a mixed number, M1 for example, M1 is going to have essentially 3 data members. M1.w, which is going to represent the whole part. M1.n, which is going to represent the numerator part. And M1.n goes all the way back to the rational data members, because we are calling the init method on rational. So if we go to rational all the way up here, we notice that rational has data members n and d. So that means that MixedNumber has data members n and d. This is going to be n, this is going to be d in this case. But it also has this self.w, which is going to represent the whole number. Okay, so hopefully that makes sense. Just to reiterate, you can represent this mixed number however you want. You could represent it as we did up here, where it's just one rational. And then you could redefine methods to do to extract the whole number part and then print it out later and things like that. But I just thought that this might be more self-explanatory to just keep the whole part and then have the rational part separate. Okay. So this mixed number is going to be represented as something like 1 plus 5 over 7, for example. So that means that we should probably redefine our str. So notice that in the other subclasses we created, WholeNumber and StringRational, we've never redefined this str method. So by default, the str method, whenever we printed a whole number, was the str method that was used was the one from rational. But since we have a whole number, which has a whole part and a fraction part, it would probably be wise to redefine it. Otherwise, we're not going to get, a good representation of the mixed number part. So in this case, we should say return, and here we want to write the whole part, self.w plus the plus string character, plus self.n, which is the numerator, plus the division, and then finally plus self.denominator. Like that. And I just remembered these should probably be strings because cast to strings because they're integers right now. Like that. Okay. So now when we do M1 equals mixed number and then print M1, let's put it back down here, we should get 1 and 5/7. Perfect. Okay, so that, notice that since we overloaded or redefined the string function in mixed number, this is the function, this is the method that gets used when we call print on a mixed number instead of the rational one. Okay. So what happens if we were to create a mixed number M2 313, for example, print M1, print M2, M3 is equal to M1 plus M2, print M3. What would happen here? Let's see. So 1 and 5/7 is M1. 3 and 1/3 is M2. This is printing both M1 and M2. M3 is equal to M1 plus M2. That is correct. That is not correct. Sorry. Is it correct? No, that is not correct. So addition between mixed numbers, we cannot, just because of the way that we represented the mixed number with a whole part and a rational part, we cannot simply use the rational add methods on it. So we will have to redefine redefine our add, subtract, multiply, divide. In this case, I'll just redefine add, and then you can see how to redefine the rest in a very similar manner. So when we add two mixed numbers, we're going to add the number itself and other mixed, like that. Okay. So now when we add two rational numbers, two mixed numbers, sorry, what happens? So how can we add this? So we would add the rational parts together, just like just regular. We can simplify them, and then we would have to extract the whole part and the remainder, right? So, okay, so I think, so first we should add the rational parts together. So new numerator is equal to self.n times other mixed .d plus self.d times other mixed .n, and new d is equal to self.d times other mixed .d. Okay, so this is the new numerator and the new denominator for the rational part only of the number. So now we can create the rational number, rational with new n and new d. Okay, so now in our hands we have this variable r, which contains the new rational, which contains a rational number using our rational class, which is the addition of the two rational parts of our numbers. So just in case this rational part is, is not in its simplest form, we can say rs is equal to r dot simplify. Okay, this calls the simplify function of the rational class that we defined on this number r that we just calculated here, and stores it in a variable r underscore s. Okay, so now we have a simplified form. In order to add, with the simplified form, we're now going to extract the whole number part and the leftover remainder part of this of this number, because it might be, if it's a fraction less than, where the numerator is smaller than the denominator, that's fine. We don't need to, we don't need to worry about it. But if the numerator is greater than the denominator, we should, since this is a mixed number, convert it to a whole part and a fraction part. So in this case, extract whole part and remainder part from r underscore s. So this is where integer division comes in handy. That's true. Yeah. Okay, so I got a comment. I will continue with this and then I'll, wait. Oh yeah, okay. Sorry. So So let's continue with this, and then I'll make a small comment for how we can do this differently. So we want to extract the whole part and the remainder part from rs. This is where integer division comes in handy. So integer division, if you remember, was this issue that we ran into a long time ago at the beginning of class, where if you divide two integers, like 1 divided by 2, for example, and you don't cast one of them to a float, the result will be 0, because it should be 0.5, but since both are integers and you're doing integer division, you're cutting off everything after the decimal point. So this actually comes in handy. The thing before the decimal point is this whole number part that we're interested in. So whole is equal to, this is where we do rs dot n divided by rs dot d. And typically, to tell other programmers that you're intending to do integer division, you usually do // It's not necessary, but this avoids other programmers, being like, did they really intend integer division or not? In this case, it's easy to determine that we intended that, but just to be sure, we can put //. The fraction part, which is the remainder, we can just use the remainder operators, rs dot n %. The percent is the remainder operator, which tells us how much more is left to get to that number after dividing it by the denominator, rs dot d. So now with this, we have the whole number and the fraction part. So we can just return a mixed number. In this case, the new whole part will be whole plus whole the fraction being the remainder, and the denominator remains the same, rs dot d, since this is a simplified version. Okay, so let's test this out now. Okay, so 1 5/7 plus 3 1/3 should not be 1 1/21. It should. So there's a little issue with 1 here, and this I think is correct. 15. We could probably use easier numbers. 1 1/2. 2/3. Let's use these numbers. 3, 6. 9 and 9 divided by 3. Something's wrong with the math, I think. Let's see. So it should give me 4. Wait, 3 and 3 plus 3/3. What is that? I see. Sorry, I wanted to do 2/3. Let's try this. So this should be 3 plus 4, 7 sixths. That is correct. And 7 6ths is correct. So there should be another. So that correctly creates the fraction to be 1 1/6. So 1 1/6 is actually just half plus 2/3. And the other things, the thing that I have left to do is to add the whole parts. So I have to do whole plus self.w plus just for, sorry, let's do total whole is equal to whole plus self.w plus other mixed.w. Okay. And that should be easier to see. Total whole, like that. Okay. So now 1.5 plus 3 2/3. The two fractions give us 1 1/6. And the whole parts will give me 3 plus 1 plus the 1 from 1 1/6 is 5 1/6. Perfect. Okay. Okay. So notice this mixed number was a little bit more complicated because we had another data member for the mixed number. Now there are many ways that you can rewrite the addition, the special functions for this class. I guess I chose to do it this way. You could also maybe create a whole number. You could create, you could create new whole numbers and add those to the rational. So you don't have to go into these, this is, I guess, slightly more low level, but yeah. So I think that's actually all I wanted to go through. I think this demonstrates how to create a class. We created this rational class. We implemented some special functions, sub, multiply, addition, divide here, so that we could use the, the operators that we know more intuitively. We also created the simplify method. The simplify method is not a special method, so we just call it using its name, simplify. Inside simplify, we looked up to see if there was, anything already written. Was there a module that already implemented something that we wanted to do? And there was, for this greatest common divisor. So we just used that. And then we did a couple of subclasses. So we did the StringRational, which allowed the user to input, to create a rational number using a different way. We'd had to do a little bit of work to parse a string, but essentially we just created another rational. So everything that we could, all the methods that we had done on a rational could be done on a StringRational. Similar thing with WholeNumber. And the more complicated one was this MixedNumber class, which inherited from rational. And here we created another data member for it, which was an integer, and then we also had the last data member, a second data member for it, which was a rational number. So we reused the rational class. We had to overload the string to print out the mixed number in, in a form that we wanted to, and we also had to overload the add, and further the subtract, divide, etc. So I think that's it. So this is just one way that you can write these classes. There are many ways to implement it as long as it returns the correct result. There's no wrong way to really implement it. And there's a lot more functionality you can add to these. So we added just plus, divide, multiply, subtract. You could add less than, greater than, and you can, as long as you write in doc strings and you document how you're doing it, I think anyone could use these classes by reading your doc string and and these would be pretty useful classes. So thank you for joining. Hope this was helpful. Goodbye.